So good morning. Today's lecture will be about mappings of tensors. Mappings of tensors induced by mappings of manifolds. So we already know what are manifolds, and we already know what are tensor fields, tensors and tensor fields. So manifolds are like that. Well, I stress that mapping of manifolds means mapping of the points of the manifolds. Yes, so any point M goes somewhere here to Fm, and altogether all points are mapped. But this is not the most interesting thing concerning mappings, because more important objects are geometrical objects living on these manifolds, and it turns out that whenever you map the points of the manifolds, that is the manifolds themselves, there is automatic mapping of geometric objects living on these manifolds, and this is very interesting for us. In particular, the most important class is that there can live tensor fields on these manifolds. There are also other quantities, but this semester we will not mention them. But tensor fields are the most important objects on manifolds for us. And it turns out that whenever you have a map of one manifold to other manifold, the tensor fields themselves are induced to map. Yes, they are mapped also. And this mapping is induced by the mapping of the points. So it is more or less automatic. You should just discover it and compute how it works. I will show it first on the simplest example. And the simplest example is 0,0 tensor fields. So we have 0,0 tensor fields that is functions. So we can have functions on any of these two manifolds. And what it means to have a function on M? It is an arrow, some psi to R, and here will be some chi to R. It is a function on N. Yes? So function from a manifold to real numbers is a real valued function. Now the question is that if we have one of them, if we can construct another one, not the one which is here, but some another one. What I mean that, for example, if we don't have this function, we just have function on manifold n. Is it possible to construct canonically some function of m? What does it mean? To make some arrow from here to here. Yes? And oppositely, if we have only this function and not this one, is it possible to construct function of n? That means some arrow from n to r. Yes? I will write without these symbols, just m, n, f, here psi, r, chi, chi, r. And now the question is whether there is some mapping from m to r if we have mapping from m to n and n to r. And it is clear that composition makes the job. Yes, the composition, first f and then chi, is a function going from m to r. directly, so to speak. Yes. But, so, here is yes. And here, in this picture, so maybe without this, yes, is better. That if this exists, also this exists. But here, the question is there some mapping going here? And the answer is yes, if this can be inverted. But this cannot be inverted in general. If you have a general mapping, and we now study general smooth mappings. So a general smooth mapping cannot be inverted. That means it cannot be used in this construction. So the answer is no. So we can induce a function on M from a function on N, but we cannot induce a function on N from a function of M. Yes? So we will simply forget this possibility, it doesn't exist, and write once again the successful possibility. Which is just the composition of mappings. And we can write it in such a way that from this function and this mapping, we will construct another function which is defined by this composition. So here it is meant that there is some operator or some grinder to which you give this function chi, and you produce this function f star chi. Yes? And it is done in this way. Yes? So it is some operator on functions which depends on the mapping f. For different mapping f, this operator is different. For still the same function. This is called pullback of chi with respect to f. So, very important word in differential geometry and more or less in mathematics. So, what does it mean exactly, this pullback? That in which sense it is pullback? In the sense that the points are going to the right, from the left to the right, yes, on this picture, M to Fm. But we see that the functions are induced in opposite way, that if we have function here, it can be pulled back, and now it is a function here. Yes, not in the same direction. This means this pullback name for this operation. That it goes against the mapping. Yes? The mapping goes in this way, and functions goes in this way, against f. So it is pulled back. We will see some other possibilities where the objects go in the same direction, and it will be called push forward. Then it is so push forward is in the direction of f, and pull back is against this f. Now you see that it is extremely interesting operator that just compose it with your mapping. So we can study some properties of this operator, and it turns out that it has a lot of nice properties. In spite of the simplicity of the definition, it has a lot of nice properties. Not to forget anyone, well, for example, if it is applied on, or first, what is this coordinate presentation? Because chi lives on n, so imagine that here are x's and here are y's, possibly different number. So f is in coordinates, xi goes to yax. This is the coordinate presentation of the mapping. Now, chi lives on n, so it is a function of y's, naturally. And what is this mapping in coordinates? This mapping sends x to something, first by f, x's to y's, and then by chi, y's to r. Yes? So, this, as a function of x's, is chi as a function of y's, and y's as a function of x's. It is just composition in coordinates. Completely trivial. And now we can see from these facts, for example, what happens if we have linear combination chi1 plus lambda chi2? Or what happens if we have a product of two functions? So, do it yourself here and show that it is a linear operator. It is R linearity here. This is from R. And, well, I will show here this something like more complicated but very easy, that it is given by this formula. So if we do pullback of a product of two functions, it is product of pullbacks. So these two operations commute. How to prove it? Simply compute it on some argument. The argument for both sides is some n from here. Yes, because it is chi1, chi2 are functions here. Their product is still function here on n, but their pullback is a function on m. So this function, when evaluated on m, is by definition is here, it is the product chi1, chi2 composed with f and computed on m, so on m, fm. In this way now. Yes. Now, what is the definition of product of functions? It is pointwise product, so it is chi1 evaluated at fm multiplied by chi2 evaluated on fm. And this is f star x1 at m, and this is f star chi2 at m, and this is the product, this product at fm. Sorry, yes, at fm, at m. So it is just put argument there and everything is clear if you remember older definitions. Yes, definition, what is composition, what is product of functions, and so on. And also, an useful and interesting formula is what happens if you compose mappings. So, if you have three manifolds, and if you have composition of mappings, that means first G and then second, then F. So you can pull back function, you have three possible pullbacks here. Functions from S to N, functions from N to M, and functions from S directly to M. Yes, by three mappings. And it is trivial, check, sorry, that this star is G star composed with F star. So apply it on some function and you will see. So what is interesting now? That the technical rule, how to do it, it is very important in mathematics to gain always for this manipulation some simply without thinking to do it. Without thinking to do it means put the star on both, but do not forget to reverse them. This is typical for pullback. We will have pullbacks in much more general situations, and all pullbacks which will be done have this property. I will see whether there is still something important. Maybe just to tell that if this is true, what does it mean that we have two algebras, functions on M and functions on N, which are these tensor fields. Yes? And the pullback goes in this way. Yes? And this is an algebra, so it has the possibility of doing linear combinations and products, bilinear products. And this says that it is a homomorphism of these algebras, that it preserves the structure. Yes? It preserves linear combination, so it is linear, and it preserves even the product in this algebra. Now we'll go to the second possibility, and they are vectors. So we already know that how 0,0 type tensor fields act when points are mapped. Yes, that 0,0 type tensor are also mapped. They are mapped by pullback, so they go to the left. Naturally, yes, we also tried them to go to the right, but it was unsuccessful, remember. So the only natural possibility here is this pullback going to the left. And now we want something like mapping of vectors. So now we go to the case 1, 0. 1, 1 is already solved. And it turns out that here it should be done not on the fields, but on the vectors themselves. Yes, so here it was done by functions which are tensor fields of type 0, 0. But here it is necessary to start with individual vectors. So let's imagine that this is some vector which will be interpreted as gamma dot. What does it mean? That there are a lot of gammas equivalent, that means tangent, yes, in this point M. Now there is a mapping to manifold N, and it turns out that we can define naturally a vector at the point Fm. And how it can be done? it can be done at least in two ways, which look completely different. One of them uses the knowledge from the 0,0 case. I will say it as a second possibility. And the first one, which has some new idea with respect to the 0,01, that here we have these gammas. Choose one of them and map this gamma in terms of f. So this is f gamma. It is mapping of gamma of the curve gamma in terms of mapping f. Because there are points, so f is able to map points. Now, here we have also some tangent vector defined by this f gamma. So it will be f gamma dot. So the mapping gamma dot goes to f gamma dot is a mapping from vectors in M to vectors in Fm. And it is called F star again, but the star is as a subscript, not superscript. And it is called push forward. It is push forward of this vector V with respect to this mapping F. Now, what about coordinates? This gamma is on the left, so it is some xi t. Now, the mapped gamma is on the right, and because of this composition of these functions, something like here, it is what? It is yat, it is some curve, yat, but it is actually ya as a function of x, I as a function of t. It is composed. Now, this gamma dot is xi dot at 0 and derivatives. It is the tangent vector to this gamma. F composition of gamma dot, by definition, is ya dot 0 derivatives with respect to y's. But we can compute this ya dot 0 now, because we see how is it constructed. It is here. In order to produce the derivative with respect to t at 0, we should first make derivative of y's with respect to x's at m, and then x's with respect to t at 0. So what we see that if we call this vi, yes, they are components of this original vector. Call this v, it is also here, yes, and call this w. So this is wa. So we are doing mapping in components. Vi derivative with respect to I to wa derivative with respect to a numbers. Yes, vi numbers, wa numbers. And now What are these numbers? We see it here. It is Jacobi matrix, JAI, which is a constant matrix evaluated at M and multiplied by VI. So the mapping in just coordinates is that these coordinates of vector on the left go to these coordinates on the vector on the right. What we see immediately, that it is a linear mapping. Yes, it is very important. So, from where it is this mapping is a mapping from vector space sitting at M, Tm, M to T, Fm, N. It means, in plain English, that it takes a vector at M and gives you a vector at N, at Fm, yes? But what is important, we see it from this formula and also some abstractly, that it is a mapping from one linear space to other linear space, and it is linear, yes? So it is a linear map between two linear spaces, constructed out of general F, which has nothing to do with linearity. It is a manifold general F. No word about linearity. Makes no sense, actually. But this F star, this push forward, is a linear map. It has also a lot of properties similar to this case. For example, if we have Fg, we get F star G star. What is it? Three manifolds. First G here and F here. So we have first vector, second vector, and the third vector. Here we have a mapping, this Fg. So if we apply on V these together, yes, it goes to F composed with G, M. Here it is sitting in M. It is FGM as point now, yes? Here is GM, and here is F of GM. And now if we apply this on any V, it is the same whether you do it in one step or whether you do these linear mappings in two steps. First, linear mapping from here to here, it is this one. Then apply on the result F star going here. Yes? And you get the same as doing it in two steps. You can compute it easily. Yes? And also it makes sense somehow without computation. But notice the difference that here star goes to both guys, but they are not inverted in comparison with pullback. So pullback and push forward differ, at least in this property, that whenever you do pullback of anything, we will have other pullbacks also. If you do it on a composition, do not forget to reverse the order. Otherwise, first, it makes no sense if you draw a picture, and second, it is not true simply. Now, why we started with pointwise construction and not directly with vector fields? Because the analog of functions should be vector fields, not individual vectors. Yes? Because it doesn't work in general for vector fields. And what are usual? There are at least two problems. The first problem, which is smaller, that in general this mapping is not a diffeomorphism, but it has, for example, this property that it is not surjective. It may happen often, yes, that our f is not surjective. Then what happens? If here is a vector, a member of a vector field, it is some m, here is somewhere fm, so we will have an arrow here, but we never will have arrow here, because it cannot come from this construction there. It is out of the image, yes? So, if here is a vector field, by this construction we will obtain vector field not on the complete n, but only on this image space, image manifold. Okay, but this is much more serious obstacle, namely that sometimes happens that it is not injective, often happens. That means that M1 and M2 go to same Fm1 equal Fm2. It happens often, yes? Now, if we map this arrow by our f, by f star, of course, and here is other vector from this vector field, we also do the same construction, and what we in general obtain here are two vectors. There is no guarantee that the push forward of this and push forward of this give you the same image. Yes. So in general, we will have several vectors, several different vectors at the same point, at the image manifold, and it means that it is not a vector field, because a vector field should be just one vector in each point. Yes. So this is much more serious than not to have vectors here, that we even have no vector field in this case. For very special these mappings, f, it doesn't happen that some very special f's have this property that whenever there are several points that, which are mapped to the same image, also vectors go to the same vector by some miracle. It is the very nice property of this f. It doesn't happen in general f. If this happens, for given f, if you find a vector field with this property, it is called parallelizable vector field or something like that. And then you have a nice vector field on the right for this very special case. And this vector field f and its image, v and its image f star v, are called f-related vector fields. This field and this field is f-related. That means this f relates them somehow. They are sitting on two manifolds and they are related by this f. But this is exception. Yes, they are in some very special, interesting situations. They are related, but we are now studying general case. And in general, we see that if you have a general vector field, here a general smooth mapping, you will not have a vector field on the right. So do not do it. Yes? So it is such a big drawback of this mapping. We will see that when we go to higher pullbacks of higher tensors, this drawback is not present there. So in this sense, it is usually told that pullback is better than push forward. It is safer in some sense. that we will see that pullback is safe whenever your f is smooth, it is perfect. So now we'll go to pullbacks of directly fields because it works. Pullbacks on 0, 1 first. So pullbacks of covectors. A general mapping from M to N. And we have some covector field here. It can be also done by in pointwise way, but I think that I will do it directly in this way. And here we will have a pullback of this alpha on the left manifold. Yes. So observe that f goes to this way, in this way, and this pullback goes in this way because alpha is here and f star alpha is here. And notice that it is this star is as a superscript. That means always that it is a pullback. Yes. So there is a notation whenever you see star as a superscript is a pullback with respect to this f, and whenever you see it down, it is a push forward. So what is the definition? By the way, I forgot to give you the second definition of push forward. I will do it in a moment, not to do it now. So we want to define this guy. First, imagine that some m goes to fm. So I see that after all I will do it in a pointwise way. So imagine that alpha is in this point. So alpha is a covector field, but we will take into account its value at fm. So first, it is pullbacked to m by definition. So now this f star alpha sits in m by definition. If it should be a covector at m, it should eat vectors at m. So we need to define this, where v is a vector at m. And the definition is that it is alpha on push forward of v. So here you have our v, here we have push forward of v. And now we can do two things. We have a covector and a vector at m, and we have also a covector and a vector at fm. Yes? So we can create two numbers. The first one is on the left-hand side, and the second one on the right-hand side. The definition is that they are the same numbers. So it is definition of this object here, of pullback of covector. Notice that in this definition, you should already know what is a push forward of the vector. Yes? So this definition is based on the preceding definition of what is push forward of the vector, which is nice. In this business, we just interchange definitions, that a new definition is based on old definition and so on. Now the question is it, the only question is it linear in V? If it is linear in V, it is really a covector there. So imagine, where is V on the right? Here. Is this number linear in V? The answer, yes, because it is a composition of two linear mappings. The first linear mapping is F push forward. It was proved that it is linear. And the second linear mapping is sitting on the right slot of the canonical contraction, yes, canonical pairing. So there are two linear maps, F star and the right slot, combined, composed, so it is a linear mapping altogether. So it is check of the fact that it is well defined. Now we want the analog of components, that how to compute it in components. So alpha is sitting here. It is some alpha A y dy A. F star alpha is a covector field on the right hand side, on the left hand side, here. Here we have x's, here we have y's. So it should be F star alpha I x dxi. And the only question is, what is this? Yes. For given alpha A. And what given? Given F. So what is it by definition? It is F star alpha at evaluated at basis vector, as usual. Now what is this? By this definition, what is a pullback of alpha? It is alpha itself evaluated at pullback of this. And it was written, well, we had this formula that push forward, put Vi to J A I Vi. So altogether, Vi with a basis goes to GAI Vi with the basis. And because it is the same Vi here, yes, it can be written like that. This goes to JAI derivative with respect to I. So this is push forward evaluated at the basis, which is enough for linear mapping. Now we need this formula here, that it is GAI and this basis. So it is GAI, and what is here? Alpha computed at vector 8th basis vector, which is by definition 8th component of alpha. So what we see that the F star alpha is JAI alpha A dxi, or in full F star of alpha, which is here, alpha A dy A, is JAI alpha A dxi, which can be, once again, because this is the same, written without this, so-called on the basis. Maybe I will write it here. The result F star, so without this, yes, it is f star or applied on the basis is JAI dxi. So what is important that it is also a linear mapping. These are two linear mappings. This is mapping from Tm to Tfm, Tmm, Tfmn, and this is a mapping of Tfmn star to Tmm star. So the vectors at the left-hand side goes to vectors on the right-hand side. And here, the covectors on the right-hand side go to covectors at the left-hand side. They go back. So this is the way of moving of this object. That vectors are going at the same direction as the mapping, as point, and covectors are going in the opposite direction. That's why it is called, the first is that push forward in the same direction as the f goes, and covectors pull back. You can see this terminology, for example, in England on the glassy doors, that pull and push, or pull back and push forward, which means that their education in differential geometry is extremely high in the whole population, that they understand that what to do when they see mathematical terminology. It is fascinating for me. And now we will go to a little bit more general case, that zero, or I forgot to do the function, so the function, yes? The 0, 0, 0 again, the second way, not 0, 0, 1, 0, yes, 1, 0. So the first was in terms of curves. The first that gamma and f gamma and so on. The second is that if you already are able to pull back functions, we have several possibilities. That imagine that this is a vector v, and you want to define this vector, this guy, yes? So we can now use the second definition of what is a vector. In the first picture, we use the first definition of what is a vector. That is it is a class of tangent curves, yes, mutually tangent curves. Here, we can use that vector is a derivation of algebra of functions. It is completely different definition, but we know that it is equivalent. So, if we have this vector, we need to say that what it gives on some function, if it is applied on some function, it should give you some number, because it is a derivation which gives you a number. But we want to define this. So we also need to say that if you have some function here, so what this vector does when it is applied on this function. If you know this answer and it obeys all properties, it is a vector. This vector is a derivation which is something like derivation along some curve. Yes? Now, we can pull back this function with respect to f here. So this function is pulled back and it sits already, or it lives already here. So we can apply this given vector on this function. Yes. And now the definition of this vector can be done in this way. That this vector acts on any function psi like this vector acts on pullback function by definition. Yes. You can do it either theoretically or in coordinates, and you can check that this definition gives you the same result as the first definition. So there are two equivalent definitions, once again. Like in vectors, we had several possibilities, but all of them were completely equivalent. So also these two definitions of what is push forward of vector are completely equivalent. It is a simple exercise. It will be given on recitation. It is some number of exercise. I don't remember. I can have a look. It is number, where it is, 50, yes, 312. In this exercise, one of several points is the proof that this definition and this first give you the same. Now we go to this 0p, and then we will go to the most general case with some restrictions. This can be done for any, still for any smooth mapping. Sorry, I will go back to show you that, or I will show it at this general case. So the definition. Let's have a tensor or tensor field directly 0p on the right manifold. Yes? Again, Mn. Maybe the pictures. Here is M, here is Fm, and here lives this tensor field. So we will define pullback of this tensor field. Which is sitting at M, if we are doing it in a pointwise way. So what is, by definition, this is the tensor of the same type. But same type, the first, the t is here, and this pullback is here, but it is also 0p. So because it is 0p, it needs p vectors as arguments. So covector is just a particular case where p is 1. And the definition is exactly like for covector, that take this t and put inside not v and w, but their push forwards. So the question is it correct definition? Does it define really a tensor of type 0p sitting at M? So what we should prove, whether it is by multilinear, yes? So take any one, for example, the last one. Is it it is linear in W with constant all others. W is here. There are two linear mappings. First linear mapping, and this slot is the second linear mapping. So at the end we see that these two numbers behave linear in W, yes, both of them. So we can use it as a definition, or this is linear, so we can use this as a definition, and it will be linear, this definition. So it is okay. Yes? It produces from 0p tensor sitting here, it produces a 0p tensor sitting here. Now, what about components? The original one is, because it is 0p type, it in coordinates it is given by this decomposition, and its pullback, because it is the same object on the left-hand side. That means in a part of the manifold using coordinates xi's, it is this guy ij dxi dxj. Yes. Now the question is, what are these components which define this tensor completely? By definition, it is ft computed on the basis. Now take this definition. It is what? It is t computed on pullbacks or push forwards of this basis. What is this? We know it from the definition 0,1, that it is ji a derivative with respect to a. What is here? It is jb derivative with respect to b. So what is it all together? Put these constants outside. jai dots jbj, t evaluated on the basis, the second basis, which is tab. So we see that f star t is these coordinates jai, jb, j, then tab, and the basis dxi, dxj. And what is t? What it was? tab dya dyb. Again, the same thing here and here. So the rest is also true without these terms, which says that if you pull back the basis, just the basis of these tensors, you get jai, and I will now put these j's to these basis elements. Either you can write it with j's completely in the beginning or here. But it is interesting that it is pullback of dya. This is the pullback of dyb. So we see that pullback just goes to each number of this product. Yes, it is pullback of the first multiplied by tensor product by the pullback of the second, and so on. And if you use back, I will put it in the exercise because it is very important to do it in detail, that if you also turn into account what happens with components, then you will see that also the components are actually pullbacked. I do not explain. They are functions of other variables actually. They are pullbacked. So the pullback term also is valid for all terms, not only the basis but also the components. And it shows that if you act by pullback by any tensor product of 0p and 0q tensors, then the result is that it is pullback of the first one multiplied by pullback of the second one, which is extremely useful fact and important. And also pullback of any linear combination is linear. Here it should be 0p and also 0p in order to make this linear combination. Yes, but these two tensors which are multiplied tensorially, they can be of any 0p and 0q type. So you see that it preserves the structure of tensor algebra, so to speak. I don't remember whether I introduced it here, but that linear combination and tensor product are preserved by this pullback, which is very important and very useful for computation. So I will try to summarize what we did yet, and then we go to any PQ. Well, we studied also 0, 0 first. Here we see that it is pullbacked, and there are no problems with no surjectivity and non-injectivity, that any smooth maps work and it is without any problem. Vectors can be pushed forward, and there are problems if the mapping is not surjective and not especially non-injective. Yes? So there are problems for fields now. Now 0, 0, 1 I didn't discuss, so let's do the same. Are there the problems with similar like with vectors? And it also will happen then for, or be true for 0p. So imagine that we have these problems, the problem situation which we had with vectors, that there are 2 points, M1 and M2, with the same result here. And when two vectors were here and we did push forward, it was a problem that two vectors came here and we have no vector field. Now imagine that we have a covector. So what happens with a covector sitting here? It goes also here and also here. But there is no problem that you have two covectors in one point. You have two covectors in 2 points. Yes? So this is no problem with the fact that we have no covector field. We have a covector field in spite of the fact that they go to a single point, because they are not added here, but one of them finishes here and one of them finishes here. They are not sitting two guys in 1 point, never, yes, ever, for this situation. So no problem with injectivity. Yes. Contrary to vectors. Now, so what about surjectivity? If we have something like this, what was the problem for vector fields? That we had no vectors outside this image. Yes? But this is not true in this case, because they are going back from the image, maybe submanifold, but the image goes to the back to the whole M. Yes? So even there is no problem that you have no covector field somewhere here. In each point you have a covector field, and in no point you have two sitting there or more. So you see that no problem with injectivity and surjectivity for this important case. And think it over that this case is the same, practically. It is just a little bit more complicated technically, but the idea is the same. That pullback is going to whole M, and never happens that you have two objects in one point. It is completely the same idea here and here. So, as I already told, here is pullback, here is pullback. Also, functions were pullback. Pullback had never any problem, and push forward can have problems. But you can do both pullbacks and push forwards if these two guys are not present. What does it mean? That it is surjective and injective, and of course smooth. So what is it? Altogether, it is a diffeomorphism. So, exists smooth. Yes? Also have a look here. Here it is quite interesting and important that you have the same Jacobi matrix. It is Jacobi matrix of F, which goes in this way. And in no of this formula you have Jacobi matrix of the inverse mapping, because it can be better, yes? If you have a general F, this Jacobi matrix exists, but the inverse matrix is problematic because the inverse mapping is problematic. So in both of these formulas, the Jacobi matrix of this direction is used, which is okay. It always exists for all smooth mappings. Yes? The other Jacobi matrix with here I and here J, A is not used. But if we have a diffeomorphism, they are both Jacobi matrix because you have also F2 minus 1, which has also some Jacobi matrix, and this Jacobi matrix is inverse to this Jacobi matrix. And in this case, you can define what you want. You can define also this and also this, both well defined. So for example, take a 1-1 tensor field, and do a pullback. By definition, always it is the same type of tensor field, so 1-1 tensor field. Yes, here is M, F, N, but diffeomorphic. Yes, now. So T is sitting here, and pullback by definition, it goes back, it is sitting here. So because it is 1-1 tensor here, we should compute it at a vector field and a covector field. We can now use the definition of pullback in terms of push forward, that it is T on pullback V and pullback alpha. Okay, I see that you are somewhere outside that. What does it mean, this? We didn't define pullback of a covector field. Yes? But the idea is that this is this. Oh.
Do you mean push forward of alpha?
Yes.
Because you said
oh, sorry. It is push forward of alpha, which was not defined. So I will go to define it. That push forward of alpha, yes?
tensor is from M or N?
Tensor is here. So when pullback, it is here. Initial tensor, thank you. Here should be N. You meant this, yes? Thank you. Here is tensor on N. So this is from 1, 1 on M already. And if it is 1, 1 of M, it should eat one vector field and one covector field here. And the definition is that let eat the original tensor T push forward arguments. Now we know what is push forward of vector field. And remember that for diffeomorphisms, it can be done. We have known these problems that 2 guys to 1, and there is image space is not the whole N, because it is diffeomorphism. It is a bijection. Yes? So this is well defined also for fields. And this was not defined. But now, if mapping is in this way, we call push forward something which goes in this way also. Yes? But, so push forward is motion in this way. But from here, it is pull back to me. Yes? So, push forward with respect to F, it is just pull back with respect to the inverse F. Think it over a little bit, yes? So, because both these guys exist, you can define this, because this is well defined. So, we will define this object on covectors like this object which was already defined for any F, including now F to minus 1. So, officially, F to minus 1 star alpha. And if you do it in coordinates, I will put it to exercise. Here we have some Jacobi matrix, which is Jacobi matrix of the mapping F. But here we have a Jacobi matrix of the matrix F to minus 1, which are different, yes? When we have these coordinates, now the coordinates are in the same number. So if we have some xi's going to yx, then also you can construct y's going to xi's of I, because this is diffeomorphism. So you have 2 Jacobi matrices, one of them is here and one of them is here, and they are mutually inverse. But they look JIA and JIA. They are formally different, with the property that B should be B, and similarly for AB summing. So now, for diffeomorphisms, we can do both pullback and push forward on any tensor field. You never have any problem if they are smooth, if F is smooth. Yes? The question is whether it is important. What about diffeomorphism? Diffeomorphism means if you have diffeomorphism between m and n, it means that they are the same practically. So why to study especially diffeomorphism from m to n? The most important application is that you directly write m on the right-hand side, and you will study a flow. Remember that flow is a mapping from m to m, yes? And it is smooth. And remember that flow in the opposite direction is inverse of the flow. So it is a diffeomorphism, if it exists for this t, yes? If you flow in this direction t and then go back t in the reverse direction against the integral curve, you finish in the same point. So it is a diffeomorphism, and it goes from a manifold to the same manifold. So for this mapping, you can produce both push-forward and pullback as you wish. And it is the beginning of the extremely important concept, which is called Lie derivative of tensor field. Yes, we will see it in the chapter 4, which is not very far from now, but still I want to present one concept which is still in chapter 3, and it is the concept of induced metric tensor. That induced metric tensor, very important thing, and it is nothing but a special pullback of special tensor field. Well, I will have a look whether I didn't forget something important. There are many important computations which are ideal for recitations. Well, there are some important facts which I'll mention now, whose proofs will be in recitations as exercises. And first of all, that if you have f m to m, f m to n, m to m, which is diffeomorphism, it turns out that something like that happens, that if you do pullback, then contraction of the result, it gives you the same thing like if you perform first contraction and then pullback of the result. So pullback commutes with contraction. It is straight for the simple computation, which I will not present here. It is 317, yes? So it is very important, quite simple, that it is ideal as an exercise for the recitation, but it is used often, yes? So it is very important to know that if I want to make a contraction of some tensor, it doesn't depend whether I do it before pullback or after pullback. And also, very interesting thing is that pullback commutes with D. The number of this exercise is 319. I also leave it as an exercise for recitations. What does it mean? You remember what is D? It is some operation which can be done on something with some result.
Gradient.
Yes, it is gradient. So you have a function and you do this. This is from 0, 0, m. This is from 0, 1, m. Now notice that both of them have 0 here. So we can do a pullback because 0p can be pullbacks in general. Yes? So we have a pullback on 0, 0, we have a pullback on 0, 1. So you can draw a commutative diagram. Well, Fm and T0, 1, M, or 0, 0. Here goes D. Now, here goes F star. And here also F star pullback. And the result is that this diagram commutes, which means this formula, that once again you can either compute a gradient of function on M and then pull back it, or first pull back it and obtain function on Fm. So sorry, should be M, F, M. So this pullback, we will start N and N. Yes, here is MM. Now it is okay that pullback from functions here to functions here, but also pullback of covectors here to covectors here. There are two kind of pullbacks, yes, studied today, both of them. So they are different pullbacks, so to speak. This is pullback of function, this is pullback of covectors. And now we can go from functions to covectors in both, on both manifolds. And it turns out it doesn't matter what you do first, which is extremely important, once again. Very important formula. The proof is simple, direct computation in a way. So it is what? Number 9, yes. And also very interesting formula. It is more or less number 8. That imagine that you pull back a covector on vector. So you do pullback of a function. Yes, you have a covector field, vector field. This is a function, so you can pull back the function. Now you can pull back both covector fields and vector fields. Here we see that we need diffeomorphism in order to define that. And the result is that here you make a pairing of pull-backed objects, and here you have pull-backed objects and then paired objects, and then make pullback of the result. Once again, it commutes. So what commutes? The operation of pullback with the operation of canonical pairing. It is once again some commutation of some two operations. Very simple to prove it, very useful in computations. Actually, more generally, if you have any tensor, with respect to diffeomorphisms, any tensor, and you evaluate it on general arguments. This is special case. Can you tell me that what is the tensor here? The claim is that this is special case for this. What tensor T should you put there in order to come from here to here? what tensor T, when evaluated on one vector and one covector, gives you this bracket. It was on exercise. What? Unit tensor, yes. It was present here. So this is a big generalization of this expression, very important, that here it acts like that. That put everything, this pullback. Put on each member of this expression, yes? Everywhere. F star V, F star W, F star alpha, and F star beta. Yes? So if you do pullback of this function, once again, this is a function composed of a tensor and vectors and covectors. And if you pull back this function, pull back all guys and put them together in the same way. Yes? So pull back all arguments, pull back the tensor itself, and put these pullback arguments to the pullback tensor, and you will get the same function like if you pull back the evaluated tensor on the left-hand side. So this is a simple exercise again. It is this number between them, 318. So I will not do these computations because they are simple and useful for you. It is much better to compute it yourself than to have a look at how I do the computation. That's why I do not do it, but do it because they are important. Do it yourself. So thank you. That's all.